Hi everyone. Through this presentation, we are looking to establish a short and effective blueprint to highlight the need, challenges, applications, and the future possibilities of establishing strain gauge sensor technology as a means to monitor the structural health of various kinds of machinery systems. This presentation is of course based on the poster presented by a collaborator from the ASME International Mechanical Engineering Conference and Exposition in 2020. Often we have observed that routine problems on machines, especially those pertaining to unwanted vibrations, may not only be attributed to rotating shafts or bearing designs or other operational anomalies, but also majorly tend to occur due to the structural defects on the equipment. These structural defects may be present from the beginning, say due to poor base frame design, or may develop over time. Either way, these anomalies can persist with lower frequency vibrations having an adverse effect on machine life. These structural defects mostly occur due to, say, the excitation of the base frame at resonant frequencies, which is found to be very close to the operating frequency, or the rocking and pitching motions due to the structural defects such as the various cracks that appear on the load-bearing members, or due to some kind of material fatigue, or due to the occurrence of localized corrosion of structural members. It is fairly difficult to identify these anomalies, mostly because the recent methods of identification are not only expensive but at the same time fairly cumbersome. So for instance, the current technology asks for the operation deflection mode analysis or ODS, or an experimental modal analysis using FEA tools, and or sometimes even demands the use of high-speed motion amplification cameras to try and better understand these structural defects. In essence, this whole process not only requires a good degree of skill and expertise, but also involves a requirement of certain softwares and tools, making this whole process quite expensive. So this opens up the door for alternate solutions such as those proposed on the upcoming slides. So on this slide, let's try and visualize some of the problems occurring on the machinery base frames due to structural motions. As you can see here, the red portion refers the base plate, on top of which we have the green and the blue items which refer to the driven equipment as well as the driver. The yellow block in the middle, it refers to a gearbox, and as you can see here, it is shown to have a high solid body mode while vibration on the base frame, and as can be seen in this slide, the red plate connected to the base frame is rising and falling, and this indicates some kind of a puffing action. This is highly undesirable and it is dangerous from the point of view of equipment design and integrity. So now that we have identified the need to look for alternative solutions to study the various structural problems on machinery skids, we can turn our attention towards strain gauges. I hope everybody is familiar with strain gauges. Strain gauges by definition are nothing but devices which are used to measure or indicate the strain of a material or structure at the point of attachment. Normally in the field of sensor electronics, the Wheatstone bridge setup is the preferred method. It can be a quarter, half or full setup depending on the requirements to measure the deflection in the structural elements. The strain gauges work on the principle of Hooke's law, which then needs certain assumptions. In this case, we can assume that the base frame structure is linear in nature. So that is, when the deflections occur, they are considered to be reversible. So that is, when the loads are removed, the structural elements get back to their original position, that is, they remain within their elastic limits, and that there is no irreversible or permanent damage. So that is, they don't go into the plastic zone. The working of strain gauges relies on the electrical resistive properties of the metal. That is, that the change in length of the Wheatstone setup leads to a change in resistance, and this change in resistance, even though it's minute when measured, is a direct indicative of strain at that point, which is of course reported as microstrain, which is nothing but a unit of strain. Further on, this reported microstrain value can be converted to the unit of choice for review and analysis. So let's talk about strain gauge technology. It's not something new, it's been around for a while. It has its own set of applications. So let's try and understand where is it really used. It's widely used across strain gauge telemetry systems, used to identify the torsional vibration in shafts, or more importantly, monitor the health of bridges or large buildings or say skyscrapers where sensor electronics are married together with strain gauge technology. So how the setup usually works is that strain gauges are arranged based on the direction of strain that needs to be measured along the principal axes. The selection of this arrangement or setup of the strain gauges comes from the strain map, which is generated by a software. The software essentially provides the location of the point of maximum deflection, technically referred to as the antinodal point. So essentially combining all the above, my idea or proposal is to extend the role of strain gauges and strain gauge technology to detect and study the structural defects and anomalies occurring in turbo machinery or rotating equipment, thus using it as a tool to study their health and on this slide are shown the various mathematical formulas where calculated bending moment can be used as input or at sometimes used as an output to measure strain or decipher the structural anomalies. And the whole purpose or rather the point is that these formulas can then be, depending on the need, deployed on say a full, a quarter or a half strain gauge setup where the different bending and twisting of the structural elements can be further studied. Let's now try and understand in detail how the strain gauges can be deployed to identify the problematic modes and location of anomalies in various structural elements of rotating equipment. So considering a proper layout of strain gauges is available based on the inputs from a FE model and the correct type of Wheatstone bridge has been selected, the desired signals can be readily obtained to help detect the structural weaknesses such as cracks or welding defects in order to help identify where the stiffening measures or potential solutions can be done to improve the integrity of the system. So let's turn our attention to the left side of the slide, the top left side. Let's assume that there is a structural anomaly present on this skid whose image is displayed here. In case compression and tension cycles are occurring in the material of the structural member, a strategically placed strain gauge can detect the deflections due to the change in resistance corresponding to this disturbance and then be able to report it as a microstrain value in the system. This can further be analyzed to identify the various, say, stiffening opportunities or find other probable solutions to address this issue. Similarly, if you turn your attention to the right side of the screen of the slide, bending modes or rocking modes above the ground for long shaft vertical pumps can be detected in a similar manner, where a deflection, if present, can be measured by locating the strain gauges along the pump's supports or at the gussets. So we will talk a little more on the application of strain gauge technology, continuing from the other slides, especially with regards to identifying the various defect modes and location of these anomalies in the structural members. So ideally, we've discussed how strain gauges should always be located or should be selected and based on the structural deflection, which normally comes out of some kind of an FE model. As you can see in this colored profile, which is nothing but a model of a base frame, a maximum strain or displacement is indicated. Now, if the strain gauges or strain rosettes are installed and a dynamic measurement is carried out, it can provide us real-time data. That is, the real-time health of the machine can be monitored, in this case of the base frame. And then it is possible to identify the anomaly where there is a high strain value occurring, so that in the future corrective action can be taken to prevent some kind of catastrophic or even some kind of failure on the base frame. So another interesting application for strain gauges is for them to be used as load cells. Whether it's a washer or sandwich or a vapor type load cell, several applications can be proposed accordingly. In order to help achieve machine foot integrity, especially with regards to parallelism and straightness, and ensure a proper bolt tightening, it's proposed to use washer compression sandwich type load cells. The load cell in this case, acting as a strain gauge, can help identify if there's a soft foot or a bent foot or an angled base. So if strain gauges are installed in all positions of the bolts and torqued against a fixed known value, then the change in strain across the bolts can be measured and compared to establish a profile matching that of a soft foot. The advantage? It will help ensure machine foot integrity and assembly of the equipment. This will in turn prevent any modification at site, or even worse, prevent any machine damage. Another proposed application involves deploying a washer or sandwich type load cell on main equipment nozzle bolts of high-speed machines. Assuming the adequate gauge length and proper temperature correction is made, it is possible to then measure or monitor the nozzle health in terms of loads and strains while the machine is in operation. Once unwanted nozzle strain or nozzle loads are detected, necessary action can then be taken either at the nozzles using stiffeners or on the piping arrangement to mitigate the unwanted stress applicable on the nozzles. The next set of applications of strain gauge technology involve detecting and overcoming piping installation errors and identifying and monitoring the development of cracks on machinery foundations. So let's talk about the first point, dealing with the piping installation errors. During the construction and piping installation phase, cold alignment errors often occur, along with the over and or under tightening of nozzle flange bolts, and sometimes just improper piping system design can also cause unwanted high loads to get passed on to line stoppers in the piping network. So at this point of time, if suitable strain gauges are installed on line stoppers of critical rotating machinery loops, excessive loads can then be identified or monitored and also prevented to cause the failure of the piping system inventory. Let's talk about the second point. The second application deals with the problem of the appearance of cracks on machinery foundation. Whether these cracks are horizontal or vertical in nature, they can become dangerous to the foundation over time. It also becomes difficult to assess whether the cracks are really genuine or they're benign. So in this case, if strain gauges with a larger strain gauge factor or a longer strain gauge are installed and a continuous monitoring is done, we can then identify whether the cracks are superficially present on the surface or actually have managed to travel beyond the lean concrete deep inside the foundation. Something like this becomes particularly relevant for rotating machinery such as reciprocating pumps and then obviously the bigger reciprocating compressors and their respective foundations. Accurate measurements depend on a stable, regulated, and low noise excitation source. Circuit calibration also becomes an extremely important criteria. However, nowadays it's possible to carry out calibration of the bridge quickly via inbuilt software. Moreover, in a clean environment, strain units may also consist of a built-in bridge box so that strain gauges can be connected directly to the input terminals. So now there are many OEMs on the market who have great signal processing and analyzing capabilities. Some examples are listed on this slide. The real requirement though is to try and integrate all this into a realistic and conventional monitoring system. And now there are many other softwares on the market which are also able to measure the Young's modulus of a structural element using strain gauges. So this is the application. The change in measurement can easily be then converted to a FFT spectra and damage detection can be achieved easily. Through this final slide, we are going to look ahead to the future applications of strain gauge technology. Wearable strain sensors are already being used for biomechanical and biomedical engineering services, especially when it comes to the use of orthopedic prognosis. The sensors can provide full animation of a hand or a limb movement. If the same theory can then be extrapolated and used in structural health monitoring of machinery frames, along with some real-time animation data, this can then look to turn out to be a good alternative solution to operational deflection shape analysis. As can be seen on the slide, a wearable strain gauge in a glove can report the 5 different movements or deflections of 5 different fingers. Similarly, as an application, the same philosophy can be applied to a 5 different key structured elements, thus providing a motion file of the entire structural element while it is in operation. This is of course a futuristic thought or a notion. However, this is also an interesting concept that can be delved upon and further explored by researchers of sensor electronics.